Hey everybody, it's Dr. Wood, and today I want to talk to you a bit about parametric versus non-parametric statistics and why you might want to care about this when you're doing your particular research. So, if you recall the normal distribution, this is also called a Gaussian distribution. This is a bell-shaped curve, right? Meaning that things tend to revert back to the mean, right? So I can flip a coin 50 times, assuming it's a normal coin. I may not get exactly 25 heads and 25 tails, but it may be pretty close. And you're going to see that when you're looking at these bell-shaped curve here, is that values that are closer to the mean tend to be more frequent. They're just more likely to occur. And then as we get farther and farther away in terms of how extremely different these values are from the mean, you're going to find they become more and more rare because, again, finding values that are far away from the mean become increasingly rare the further away you get. And so that's basically the generally what we're looking at in terms of normal distributions. Now, again, this is assuming that things are truly random and that they should be centering around this mean here. When you have, for instance, a large enough sample size, and say I was to flip that coin, instead of just doing one trial of 50 flips and expecting to get 25 heads and tails, which is unlikely to occur, maybe, 24, 26, something like that, you're going to find that by repeating that trial or maybe increasing my sample size, you're going to find that you will end up getting a curve that looks very similar to this. And that's because you're going to find that outliers tend to offset one another. So for instance, if I were to have one trial where I got, say, 49 heads, it would be very unlikely, but there could be a similar outlier the opposite direction, saying I got 49 tails one time. So you would see this normally occurring with a Gaussian sort of distribution. As I mentioned, that the more extreme a value is, the rarer it is. However, you're going to find that outliers, especially if you find that you're introducing some sort of bias that is influencing the values to have more outliers, that is really going to skew your numbers. That's going to change the mean pretty significantly. So remember that means are particularly susceptible to the effects of outliers. If I have one very large value or very low value, you're going to find that's going to skew your mean pretty significantly. That won't be the case when you start talking about medians and things like that. And recall, it doesn't mean that things are normal, quote unquote, like you might normally think about it. Again, I'm using the term normal like in 3 times in the same sentence, but again, this is just referring to the scatter and the fact that the data is going to be centering around this mean, assuming that everything is truly random. Now, to know whether or not the data is actually going to be normally distributed, you have to do a test for normality, right? And so that's the test that your researchers, if they are going to go under the assumption they have a normally distributed set of data, they have to show that they did this test, right? Because otherwise, if they're just assuming that it's normally distributed and it's not, and this is the big takeaway here, it tends to lead to more type 1 errors. Because when you're using a normally distributed set, assuming that it's normally distributed and you're using tests that are associated with that, you tend to find they are a little bit easier to achieve significance because it is going under this big assumption here. So if you falsely make that assumption, you're more likely to find false positives, right? You're more likely to see those type 1 errors there. So this is a big thing that you should be keeping an eye out for, is that they're going to be using tests that are associated with normal distributions. They better make sure they test for that normality there to show that their data is normally distributed. Now, non-normal distributions, and I think you'll find that in most of the medical research, you're going to see this used much more commonly because, one, we are unable to show normality. We're unable to pass that test. Perhaps we have small sample sizes, which are more likely to have those outliers without having someone to offset them. And so with these, they tend to be more conservative, right? Because you don't want to make a type 1 error, but that trade-off is there. If you reduce your chance of making a type 1 error by being more conservative in your calculations, you tend to be more likely to make a type 2 error, which again, we talked about before as being a false negative, or basically not being able to reject your null hypothesis, saying there's no difference here when one is actually there. You also tend to find this is less influenced by outliers. And the reason for that is because instead of using mean values and things like that, they switch over and use medians, and they basically will rank all of the values in that test, and that helps to eliminate the outliers. So that way, something that is ranked as the 50th, the very top of the scale, is still the same difference in terms of value away from 49. It doesn't really matter if it's an outlier or not. It's going to be less likely to skew that data there. And it gets much more complicated than that, and I might not be doing the best description of that, but just know Non-normally distributed tests, they tend to make more type 2 errors, and they are less influenced by outliers. And if you're just not sure what type of data you're dealing with, or if you're reading a study and they're not sure, you just go ahead and use non-normal distributions, because you want to be more likely to make a type 2 error than a type 1. You don't want to get a false positive. That's more dangerous in the grand scheme of things than a type 2. And again, remember, they're using medians and interquartile ranges to describe that data. So getting into your confidence intervals, recall that you want to know that confidence intervals can help you determine basically, how likely the true value, if you were to take a study and then apply that back out to the general population, how likely is it that you would find that population average within that value there? And again, we use 95% confidence intervals to say we're 95% sure that the actual population average would be somewhere between this value and this value if you were to then apply that out. Recall, though, that when you have things like smaller sample sizes, you're going to be more likely to see large ranges. If I only have 10 people that I'm working with, that's not likely to be very representative of the entire population. But the bigger my N gets and the closer that it gets to the whole population, the more likely it is going to be that I can narrow down that 95% confidence interval, and I can be much more sure in a smaller range of values that, yes, that population average will be between that. So let's say, for instance, we were doing a trial and we are just measuring blood pressures of random individuals that are walking by the street, right? So if we just have an N of 10, let's say that the average blood pressure that we got was 106 millimeters of mercury systolic. Now, we know that a normal blood pressure, quote unquote, is 120 over 80. So it would seem like this is not very representative of the population. Perhaps you got a lot of, very low blood pressure people that day. But if you look at the confidence interval, and you're then going to apply that back to the population, you would say, though, I'm 95% sure that based off of this sample, that the population's average systolic blood pressure would be somewhere between 93 and 132. Well, that's a really big change in value there. It's almost 40 points of blood pressure in between that. So it's not super useful to say, it's somewhere in there. I'm 95% sure of that, which is true. 120 is included within that, but it's not super useful there, right? As you get into a bigger sample size, so let's say we did 100, notice we're getting closer and closer to the actual average systolic blood pressure, right? By the time you're getting up to like 100,000, you're getting pretty close to it, but notice how your confidence interval would get more narrow, right? So again, the N of 10, you're maybe dealing with like a 40-point spread. By the time you get down to 100,000 people, which is quite a large trial, it's only maybe 4 points. Now, I made all of this up, so who knows what the actual data would look like, but you can get a feel for this. So the bigger your sample size is, the more narrow that confidence interval is. And again, you'd rather have a small value to say, yes, I'm pretty sure that the actual population average is somewhere between this value and this value. It's like saying, well, when's my package going to come? On anywhere between Monday to Sunday. Well, that's not super useful for your purposes if you have to sign for the package, right? But if you can say, well, it's going to be here on Tuesday between 6 p.m. and 7 p.m., that's pretty useful, right? So I just thought of that analogy, and I think I'm going to keep using that one because it's pretty accurate. Let me know in the comments if you don't think so. So then getting into the test here, remember we use parametric tests when we're dealing with normally distributed data, okay? Non-parametric tests are going to be used for non-normally distributed data, or if we're just not sure, you just go the non-parametric. Remember, non-parametric tests are more conservative, so you're more likely to make type 2 errors. If you're going with parametric test and you don't, you falsely assume that your data is normally distributed, either you didn't do the test for normality or things like that, you're more likely to make a type 1 error or find a false positive. It's easier to achieve significance with parametric tests, but you're going under a pretty big assumption there. The examples you'd see for this, and we'll talk more about tests a little bit later, include things like your t-tests, ANOVA, and whatnot. Now, for every parametric test, there's going to be a non-parametric, alternative to it that you can use. And unfortunately, their names are much more difficult to remember. I generally have to look these up most times. And so you'll see things like Wilcoxon assigned rank tests. They'll have the Kruskal-Wallis test, etc. Just know if you see these, that these are going to be the non-parametric cousins to your typical parametric test like a t-test. Everyone knows what a t-test is, but practically in the medical literature, it's difficult to use one of those unless you can show that your data is normally distributed. So that's it for this section. If you have any questions, please let me know, and I'll talk to you soon. Thanks a lot. Bye.